Yeah.
Okay, great. Thank you.
Yeah.
So, welcome everyone to our HO colloquium today by Ranodip Sarkar. Um, Ranodip Sarkar obtained his PhD in physics from the Physical Research Laboratory in India. For his postdoctoral experience, he moved to the University of Helsinki and has been working there to date. His primary research interest lies in the observation and modeling of solar eruptive events to understand their genesis and the consequent space weather effects. He was awarded a 3-year postdoctoral research grant funded by the Academy of Finland to conduct research on the numerical modeling of space weather events. He has been a visiting fellow at the NASA Goddard Space Flight Center, the Royal Observatory of Belgium, and the High Altitude Observatory. Um, so, to Ranadip, uh, will be speaking on analytical and numerical modeling of coronal mass ejections to understand their space weather impact.
Yeah. Thank you, Moshmi, for your kind introduction. So, thank you for giving me this opportunity to share my research work in this platform. So today I'll be talking about the analytical and numerical modeling of CMEs to understand their space weather impact. So to begin with, I would like to start with a brief introduction about the underlying motivation for these studies, which is based on the Sun-Earth connection that relates how the solar eruptions happening close to the sun can affect the space weather at near Earth space. So the major driver of CMEs or like the major driver for the space weather is the coronal mass ejections, which are the huge expulsion of the magnetic plasma from the sun, which routinely erupt from the sun. So how can we observe it? Like we can use the remote sensing observation to observe it. So here is an image of a CME. So typically they consist of three-part structure. One is the bright so the bright leading edge at the front, and which is followed by a kind of dark cavity-like structure here, and which is also again followed by a bright core prominence. Now, the underlying magnetic structure of this dark cavity here is believed to be consist of helically twisted magnetic field lines like this. So, this kind of twisted helically field lines around a central magnetic axis is typically known as magnetic flux ropes. Now, if we just look at this part of this magnetic flux loop configuration, so it should look like a central axis of the magnetic axis, and it is surrounded by the helically twisted field lines. Now, if we take a cross-sectional cut of this magnetic structure, and we can if we project this helically twisted field lines on this particular cross section, then it should look like a closed circular loop-like structure. So in this particular image, what you are seeing, you are looking at the side view like this. But we have also evidences when the orientation of the CM is like that, when we can observe this cross-sectional part also. And if we observe this cross-sectional part, then due to this projection of this twisted structure, we should expect there should be some closed patterns we should observe in those structures. So in reality, we could actually see this kind of closed patterns when we have a cross-sectional view of a CME, so which tells about that maybe this kind of structure actually looks like a helically twisted field lines. Now we do as we have the remote sensing observation, but when these structures erupts from the sun and they travels out in the space and they reaches close to the earth, then we have also the in situ, we can have the in situ observations of those magnetic structure. So we can have all the plasma parameters observation from the spacecraft located close to the earth. So here is the example of those observation. So where you can see, so this again, this particular cavity-like structure has a higher field strength as compared to the background solar wind. So in this, so the region bounded by this vertical solid lines is basically the magnetic flux slope that we observe at the in situ. But again, now how we can convince ourselves that it has like again a helically twisted coherent magnetic structure. So let us again take an example of, so again go back to the cross-sectional view of the flux slope, and if you just again project these helically twisted field lines on this particular plane, so the magnetic map corresponding to this structure should look like this. So now let's say this structure is passing through a spacecraft. Now the spacecraft, and let us just look at only the component which is in the north-south direction, that is perpendicular to the ecliptic plane. So as at the first point of contact, the spacecraft will see this north-south component is towards the south. That means towards the down. Now this downward direction will continue until the spacecraft reaches to the central point of the flux slope. At this particular point, it will see there is no like north-south component. It's all about the horizontal component. So so magnitude-wise, this component first will see the downward and like higher magnitude, but as it goes towards the center, it will see there is no magnitude-wise, there is no north-south component. As it pass through to this part, then it will again start to see now the north-south component will change its sign. Like at this side, it was like downward, that means southward. But at this part of the flux slope, it will see it is towards the north. So it will see a smooth transition from south to north. South means in terms of this direction from negative to positive direction. So here is this north-south component of the magnetic field is shown within this part. So here you can actually observe there is a smooth transition from the negative to towards the positive field part of this particular component. So it again tells that the like internal magnetic structure is coherent, and it looks like a helically twisted flux loop structure. So now we get to know something bit about the magnetic field structure of a coronal mass ejections. But the important aspect is that when this has a southward component of magnetic field, then its orientation is actually opposite to the orientation of the Earth's magnetic field. So with this kind of configuration, when this structure reaches close to the Earth, then what happens? Magnetic reconnection occurs at the conjunction point, and as a result, all the charged particles carried by this kind of magnetic structure enters into the Earth's magnetosphere, and then it creates a geomagnetically induced currents, so in the form of a ring current. So as we know from the Ampere's law, if you have a ring-like current, then it induces a magnetic field which is basically opposite to the Earth's horizontal magnetic field. So as a result, we see there is a reduction in the Earth's horizontal magnetic field, which is indicated by this index, which is called disturbance storm index, the DST index. So in terms of this, we can see there is a huge reduction in the DST index, which is the indication of the geomagnetic storm. So now we know, we get to know that if this kind of magnetic structure has a southward component which is opposite to the Earth's magnetic field, then it can create a geomagnetic storm that can be identified as a reduction in the Earth's horizontal magnetic field, which is indicated by the DST index. So as a result of the geomagnetic storm, we can observe beautiful auroras, which is very nice phenomena in the nature. But on the other hand, which is the dark side of the space storms, is that it can largely affect the electric and telecommunication system on the ground. So here is one example in the year 1989. Due to this induced geomagnetic current that hugely damaged the transformers in hydrocubic system, that causes the electric power loss for almost 9 hours, and it is historically known as the day sun brought darkness to us. Now, this is not only the cases in the recent year, in 2022, we have also witnessed the loss of the Starlink satellites due to these geomagnetic storms. So basically, this can also affect the satellites in the space, which serves us for the communication and navigation system. So if a geomagnetic storm damages those, so it can hugely affect our navigation system and GPS system as well. And also there are example of extreme space weather events that in the year of 1859, when there was a huge solar storm, like so in the right hand side you can see there is a hand drawn image by Professor Richard Carrington of a solar flare, which was observed on the surface of a solar photosphere itself. So mostly these are observed in the higher atmosphere of the sun in the coronal height, but the intensity of this solar flare was so strong that it was also observed, or it traced its points on the like solar photosphere itself. So this is the huge the solar flare that occurred in the year 1859, and as a result, so there was an intense magnetic storm which was registered in during the September 1859, and the and this is the biggest magnetic storm recorded in the history. And as a result, the mid-latitude areas over the United States and Europe faced a huge electrical shock and fires. Now, remember that at that particular era, the only vulnerable telecommunication system was the telegraph wire. But if this kind of event occurs in current era, then the estimated cost could be a 2.6 trillion or equivalent to something. So in order to avoid those huge economical loss, it is very important to predict the arrival, and also knowing their whether there will be what will be the intensity of the geomagnetic storm associated with those solar eruptions. So we want to predict those in advance in order to avoid this kind of economic losses. So the basic framework for this would be like should be like we have the remote sensing observations through which we can observe these solar eruptions close to the sun. So we can have a prior estimation of the of their kinematic properties, like how like what is the kind of speed they are with which they are ejecting from the sun, and what is the internal magnetic field orientation of this kind of structures close to the sun. Now, once this structure ejected from the sun, they can typically reach from sun to earth within 2 to 3 days. So within this time period, what we can do, we can use modeling tools uh, in order to predict in advance that after 2 or 3 days, what will be the final magnetic configuration of the structure close to the earth, and what will be their speed, and what will be the direction of propagation, whether they'll hit or miss the earth. And if they hit the earth, what will be their magnetic field orientation, whether it will be opposite to the earth's magnetic field. If it is opposite to the earth's magnetic field, then that will be very severe to cause the geomagnetic storms. So this is the basic framework that we do for the space weather forecasting. So I'll step by step go through that, how we can first estimate the near sun properties, both like kinematic and magnetic properties of these solar eruptions, then how we can model them from sun to earth to get some advanced predictions. So in order to do the first step, so what do we mean by the magnetic properties of a flux slope? So there are basically three properties. One is the chirality. So basically the chirality is that you can again imagine, so this is the black arrow is the central magnetic axis of the flux loop, and these helically twisted field lines around this central axis, they can be twisted in such a way that whether they can be clockwise or anti-clockwise rotating around this central magnetic axis. So this sense of rotation is denoted by the chirality sign, whether it is right-handed or the left-handed. So using the solar eruptions of these erupting structures, so if you look at the UV images, so sometimes they're accompanied with this kind of sigmoidal structures. So we can look at how the sigmoidal structures are shaped, whether they are forward S-shaped or whether they are reverse S-shaped. So depending on this morphology, we can identify the chirality of this structure. And also, if we don't have any clear observation of this sigmoidal shapes or J-shaped structure, then we can rely on some hemispheric helicity rules that tells you that irrespective of the solar cycle, like all the erupting structure that are erupting from the northern hemisphere of the sun, that should be have a left-handed chirality, and the south, uh, whether if they are ejecting from the southern part of the hemisphere, they are associated with the right-handed chirality. So they, in that way, we can estimate the sense of rotation of this helically twisted field and the central axis. Then the second part is that what is the orientation of this central magnetic axis, like the arrow of this black arrow, whether it is northward, southward, or eastward or westward. So this we can observe, or we can estimate using the one way to do it is like observing the coronal dimmings. So when the structure erupts from the sun, so this is again a cropped UV image from the on-disk observations during the eruptions, when the eruption is happening. So when this structure erupts from the sun, so through their legs, a huge expulsion of the mass is occurring there. So due to the expulsion of the mass, what happens that there is a depletion of the density at the two legs of this flux rope. So due to the depletion, what you see, there is a reduction in the intensity in the UV images. So in that way, you can actually locate where the 2 foot point or the two legs of the flux rope is attached in the sun. So once you identify these two locations, then you also have the associated magnetograms. So you can overlay these two locations on top of a magnetogram, and you get to know what is the magnetic polarity of these two particular locations. Once you know the magnetic polarity, then you know, okay, if this is positive and this is negative, so it is coming from plus to minus. So the orientation is almost southward. So in that way, we get to know what is the central axis orientation of this flux rope. Now we know the central axis orientation, and we also know the chirality. And the third part comes that what amount of magnetic flux is going inside this flux rope to finally constrain it in the MHD models. So there, so it is very difficult to directly estimate the magnetic flux because we don't have routine observations of the coronal magnetic field. But instead, what we do, we use some proxies, which is basically, so here are some examples where we use the the observations of the structure during the post flare phase. So here one example. So you can see in the AIA 304 image, so there is a filament channel, and during the post flare phase, what we see, there is a formation of the post flare loops. And if we estimate the magnetic half of the magnetic flux underlying these post flare loops, so they are associated with the poroidal flux of a CME. So in that way, we can like using this proxy, you can estimate the amount of poroidal flux, and also we can for we can use also the flare ribbon intensity to estimate the poroidal flux. So here is again one example that we can observe the AIA 1600 image to identify the flare ribbons, and we can cumulatively see that how much area is swept out by these flare ribbons and take the amount of flux which is associated to the amount of poroidal flux injected to a CME. So in that way, using these proxies, we can have also the estimation of the magnetic flux. Now once we know the magnetic properties of a flux so close to the sun, now the next part is comes that we need to model those things from sun to earth. So there are two options. One is analytical approach and second one is MHD approach. So if we use some analytical approach, then we need to know that whether the expansion and propagation of the CME from sun to earth, whether they follow some systematic relation or not. So for that, I will show you some example. Like here is an example of again like a baby flux rope, we can call it. So before the eruption, so again a cross-sectional view of the flux rope. Then so that's why you see there is a circular like structure here. So which is the basically the cross-sectional shape of this flux rope, and it is known as the coronal cavity. Now, as it erupts from the sun, we can like track how the geometry of this shape evolves with higher heliocentric distances. So here we have tracked it, and what we have found that if we look at the centroid of this of this shape, that initially it goes like this, and then it undergoes a deflection, and then it moves like this. So if we look at higher field of view, so after it has deflected close to the sun, then it like roughly maintains a constant direction of propagation. And also, if we just take the ratio of this cross-sectional shape, like for here, I am using the semi-major, the radius of the semi-major axis to the distance from the central point to the center of the sun. And if we take, if we just plot this ratio with respect to the heliocentric distance, so what we see that initially it is it is not linear, but after some point it is fixed and it is like constant after 2.5 or 3 solar radii. So this is the regime of self-similar expansion. That means in which the this aspect ratio is constant. So the beauty of this, like that, like if we know this aspect ratio close to the sun, so let's say we know this aspect ratio is 0.22, and you want to model the CME, how it is evolving from at various heliocentric distances. So let's say if you want to know the cross-sectional radius at 30 solar radii, you just need to multiply this 30 into 0.22 to get to know what will be the cross-sectional radius at 30 solar radii, because it almost remains constant. So, and also we can assume that although there could be a large deflection close to the sun, but after certain solar radii, it maintains a constant direction of propagation. So with these assumptions and using the self-similar expansion, we can using some analytical tool, we can there is a way to model these structures from sun to earth. So here is an example. We use this interplanetary flux slope simulator. It is an analytical model, again based on the assumptions of self-similar expansion, that once you constrain the tilt and direction of propagation of the flux slope close to the sun, and you assume that okay, there is no further deflection or rotation is happening in between sun and earth, and also you expand this structure just using that constant aspect ratio that comes from the self-similar expansion. So using this simple tool, what we have seen that it works well for the events or the CME events that are that shows a isolated evolution that does not interact with other CME structures or solar wind. So here is the initial validation of this. So we're using the on-disk observations like the flare ribbons we have, and the post-flare loops, and like the magnetic flux underlying these post-flare loops. We have constrained the polarized flux, and also from the other proxy informations, we get to know what are the other parameters of this flux slope. And if we just expand it self-similarly, we see there is this gray shaded, the region bounded by the red vertical lines are basically the in situ observation of the magnetic flux slope structure. There are different magnetic field components are shown here with the black solid lines, and the ensemble model results is shown by the gray shaded regions. You see there is a kind of decent match with all different magnetic components at 1 AU. And so we have also extended this work for several events where a CME is encountered by radially aligned multiple spacecraft at different heliocentric distances. So in a way, that will be a 2-point validation at two different heliocentric distances. So here are the 6 events where in the all these images are basically the ecliptic plane has been shown here. And you can see there are different spacecraft that includes a stereo, and also the spacecraft orbiting Mercury, that is the messenger, the spacecraft orbiting Venus, that is Venus Express, and stereo as well. So we have this kind of events where the CME is detected by this radially aligned spacecraft. So, and this also includes events with like isolated CME evolution, as well as the events that were associated with interaction with solar wind or any other structures of the uh, wind itself. So what we have seen for the, again, for the isolated ICME evolution, we have seen that within the uncertainty limit, that means the gray shaded region, all the like the both the field strength and also the rotation, like in the BY and BZ, these are well captured at both the heliocentric distances by this analytical tool. And what I'm showing here, that these gray shaded regions are coming basically from the uncertainty which are involves due to like estimating the input parameters, that means direction of propagation, the tilt angle of the CME. So depending on that, we can have this kind of large uncertainty. So part of the model results that are associated with the lowest impact for this particular event. Lowest impact means the distance between the spacecraft to the magnetic axis of the CME where was lowest. So for that part, we have found that there is a knife which is this cyan dashed lines, which is like more matching very well with the observed magnetic vectors. More importantly, although there are large uncertainties, but the importance of this multi-spectral event is that if you have the information of this structure also in this kind in this inner spacecraft observations, so you can use this inner spacecraft observation to constrain your ensemble model results, which has been shown here by this red dashed lines. So I have taken the ensemble model results that best fitted with the inner spacecraft observation by minimizing the root mean square error at By and Bz and also in the total V. So which we have found these red dashed lines. And if we just propagate this red dashed line using the 1 by r square, so that is the self-similar expansion, we get to see that there is a very nice match at the outer spacecraft. So as the inherent assumption in this analytical model is that the magnetic field strength follows 1 by r square. So from that, we can see, so basically if the icing evolution is isolated, it's not interacting with other solar wind stuffs. So mostly the magnetic field strength is varies with 1 by r square. But this is not the case when there is interaction is happening. So here is one example. So in the top panel, you see the observation, in situ observations from the stereo, I guess, yes, stereo this spacecraft. So where you can see, so again, the region bounded by the the dashed vertical red line is the magnetic cloud or the structure of the magnetic flux rope. And you can see in the lower panel where this is the speed is drawn. So this is followed by a high speed stream. So when the structures are followed by the high speed streams, then it cannot expand self similarly. So basically this high speed stream is pushing from the back, so not allowing the structure to expand self similarly. And also we can identify that the interaction between this magnetic cloud and high speed stream occurs in between its journey from messenger to stereo B. It didn't occur before that, like during the journey from sun to messenger. So what we have found, like at messenger, within the uncertainty limits, with the field strength is matching with the observed field strength. But if we go to the outer spacecraft using the 1 by r square law, so again, if you compare the gray shaded part with the observed part, which is the black solid line, so there is a huge underestimation of the magnetic field by this analytical model, because it cannot incorporate the interaction happening between any other structures. So what is happening there? So due to the pushing or like from the back by this high speed stream, it is not expanding self similarly. That means it is not following the 1 by r square law. Instead, if we take this index r to the power x, this x is much lower than 2 if for such cases. So if we, so for what I did, I tried to decrease this exponent and come up with this run 2 and run 3, where this exponent are less than 2. So if it is lower than 2, then we could like reproduce the field strength which is observed at stereo B. So the pink lines are basically where the exponent is much lower than 2, and even in a minus 0.5. So when it is minus, that means it's not expansion, rather than it is a compression effect is going on. So when we incorporate this minus exponent, so we could like decently reproduce the like field strength of this observed CME at the outer spacecraft at stereo B. So now from that, it is clear that analytical model could do some justice for the isolated CME events where there is it when it follows a self-similar expansion and do not undergo any huge rotation or deflection. But if we want to study these complex things, so in reality things are like more complex. So we need to go for some physics-based model, that is the MHD. So here it is this is an output from an MHD model where so basically this is the isocontours of a density structure coming from the sun. So you can see at the same time there could be many CMEs coming from the sun. They could be interacting with each other. Also, one CME could be interacting with other high-speed stream component of the sun. So we need to incorporate all those physics to properly model a CME eruption from sun to earth to get the their magnetic field orientation correctly. Like both the magnetic field orientation and the strength of the magnetic field of the CME correctly at 1 AU. So for that, we use the MHD model, which is the European Heliospheric Forecasting Information Asset known as Euphoria. So where we start, so as is a heliospheric model, so it starts at 0.1 AU, that means 21.5 solar radii. So what we do, we use coronal models to generate all the plasma conditions at 0.1 AU, and then we inject analytical flux group model from this lower boundary of the heliospheric model, and finally then using this heliospheric model, that is Euphoria, we study their heliospheric evolution from sun to earth. Now to to model the a magnetized CME, so there are two ways that one way, like if we just concentrate our aim to just focusing on the arrival time estimation, then we can just use, instead of any complex magnetized CME, we just can use a cone model, that means a hydrodynamic pulse, which can be injected which can be whose speed can be constant from the observation, and then that can be injected through the inner boundary of the heliospheric model. But if we also want to interested to identify the magnetic structure, because that is also very important for the geomagnetic storm, as I have already explained, because what the way, if its orientation is opposite to the Earth's magnetic field, so that will be our main aim, to identify whether it is oriented in such a way or not. So for that we need some magnetized model. So there are, so one of the widely used model is a spheromag model that we use to mimic a CME here. So before going to the model, so you know this so here the spheromag configuration viewed at different angle is shown here. So and also you can see there is one symmetry axis which is along this. So along this symmetry axis also there is a magnetic axis, which I call this axis of this toroidal part of the spheromag. So we observe the orientation of the magnetic axis of a CME, and we try to align this toroidal axis of the spheromag with the observed axis of the CME, like this blue part of the spheromag. So here is an example. So where we have estimated the magnetic flux and the orientation of the flux rope from the observations. And then what we have found, it is like kind of vertical flux rope with a northward directed field. So with this northward directed toroidal part of the spheromach, we have constrained our model like this. So this gray shaded sphere is not the sun, but it is the lower boundary of the heliosphere that is at 0.1 AU. So on this top, we are injecting a spheromach, and I have not drawn all the feed lines of a spheromach, which will look like a spherical bubble, but I have only plotted the field lines which is like gyrating around which are like gyrating around its magnetic axis. So basically the blue part of this particular analytical model. So this part you can see, so that it is like aligned what we have observed of flux rope orientation. But now what we have observed, that as this structure is propagating out in the heliospheric domain, so it rotates almost 90 degrees. That means from this part, we cannot, if we just look through the sun earth line, we cannot see the core part of the spheromach from here. But as it rotates almost like 90 degrees, now we started to see the basically the core structure of the spheromach through this. So in order to visualize it more clearly, so here this is the image of where I have shown that how this structure rotates from its initial insertion phase to 1 AU. So basically, from you have to follow it from right to left. The rightmost corner is showing the spheromach configuration when it was during the insertion phase. Again, I have not plotted all the field lines. So basically, it mimics the field lines basically mimics the magnetic axis of the spheromach. So the top panel shows the view which is along the sun earth line, and the middle panel shows the view from the top of the equatorial plane or the ecliptic plane, and the lower bottom, like the lower panel, it shows the view from the side of the meridional plane. So now you see in the this part, if you look from the sun earth line, so initially you don't see the spheromach core, which can be seen from the side view here from this angle. But as it moves from this to finally at 1 AU, now you start to look at the core of the spheromach. So it has kind of rotated on the plane of the ecliptic, or more accurately plane of the equatorial plane. So initially, if you look from the top, it was oriented like this, and it is rotating like clockwise, and finally it takes the shape of like this. So this kind of huge rotation, like almost like 90 degrees, we have observed for this kind of spheromach. And if there is any actual physical reason for this, yes. So recent studies have shown that, so when you place a spheromach in a background magnetic field, so depending upon whether it is stable or not, so that denotes the spheromach tilting instability. So let's say in this particular configuration, if you see the magnetic moment of the spheromach, it is aligned with the background magnetic field here. But as you just shift this structure, if there is a mismatch in the orientation of its magnetic moment with the background magnetic field, then it is in a metastable condition. So it then tries to go back to the stable condition and takes the shape up like this. So when we launch the spheromach in the heliospheric domain, if there is a mismatch between the magnetic moment of the spheromach and the background solar wind, then it falls in the metastable state, and it tries to rotate in its in such orientation so that it again come back to the stable condition. So that was the main reason when we launch this kind of structure in the heliospheric domain, it start to rotate. Now, then we have also examined that, okay, if we just change the density of the spheromach, like if we higher the density of the spheromach, what kind of effect that then we can expect? What we have seen, that if we just increase the density of the spheromach, we can see the rotation is very less for the massive spheromax. So here, this is the plot where we have shown with the higher heliocentric distance how the rotation is happening. So for the low density spheromax, although it is almost like 90-degree rotation, but for the high density spheromax, which is one order of magnitude higher than these red ones, so we see there is very much less rotation. And also, if you just look at the heliocentric distances, so the major rotation is happening below 0.3 AU. We know the magnetic field strength of the background solar wind is much higher close to the sun. So that means the severe rotations are happening below 0.3 AU. And why we are getting less rotation for the higher spheromax? Because for the heavier spheromax, it is hard for their moment of inertia is higher. So that means like for the background magnetic field, it is hard to rotate those heavier spheromax to extent of large rotation angle. With this also what we have found, like now if we just compare the spheromax structure with the in situ observations at 1 AU, so then here is the comparison we are showing. So here again the black solid lines are the in situ signatures of different plasma parameters at 1 AU, and the red lines, the red solid lines are the model outcomes from the model with the euphoria. So again, I want to remind you that in our classical picture, where the flux looks like that, their two legs are attached to the sun and they are helically twisted like this. So in that particular configuration, if we just take, let's say our spacecraft is crossing this structure from here to here, what it will see that in the direction of the like north-south component, it will see there is a unidirectional north-south component, because that will be like a positive throughout its crossing from this point to that point. So here we in the observation we also see the BC component is unidirectional, so which is mostly which is purely northward from this point to that point, which is basically the two boundary of the flux loop. But if we see our model results, which is the red lines, so red solid lines, which is initially positive. So here you can see there is early arrival of the flux loop with respect to this structure. So initially it is positive, which can be matched with this positive observed structure, but then it goes to a negative thing. Like initially it is purely positive, then again it is rotates like negative here. So why this is happening now? Because in our case the spheromax structure, it don't have any legs attached to the sun. So so the flux loop, so the spacecraft will see this first this part where your like north-south component is positive, but when it will but again it will encounter this part also, where the north-south field component will, because this is a rotating structure, so at this part the northward like north-south component will be southward, so it will see a negative part when the spacecraft crosses through this part. So that's why in our modeling we are getting this negative part, because our structure is not attached to the sun. We are getting the this part as well as this thing also. So basically, if you want to like compare one to one, so this part, only this part of the structure should be compared with the observed thing, which is basically denoted by the gray shaded region, where you see the purely positive part of the spheromax. So this part can be compared with this part, but not this lower part. So that's the kind of like how we can compare a spheromax structure in our model with the in situ observations. And what we have also seen that due to this kind of structure, like this kind of detached structure, and when it also undergoes a huge rotation, then also we have a huge uncertainty in the busy prediction. So so it is shown here. So again, if, for the uncertainty analysis, what we have done, we have placed, in this particular thing, this is a plane which is on the ecliptic plane, and the colors show the north-south component of the magnetic field. So if we again just recall the spheromag structure, so this has undergone a huge rotation. That's why you see, so this structure, like one magnetic axis is going through this point, and another magnetic axis is going through this point. So essentially, you are getting up two opposite polarity side here and there. So if we just look at different spacecraft at, let's say, within plus minus 15 degree, so maybe one spacecraft may encounter a totally different BZ, and another spacecraft which is in purple that may encounter a totally opposite BZ. So within this kind of spacecraft, you can see there will be a large uncertainty registered at 1 AU. But when the rotation is very minimal, so then what will happen? So on like this positive part will come to the spacecraft first, followed by the negative part. Now, if we just look at take now in this particular case, all the spacecraft will see only the positive part is coming, and although the negative part will come, but that will come later. But at the initial point of contact, all the spacecraft will see the only the positive part is coming. So if we just drawn this positive part encountered by this different spacecraft here, it all will see the only the the positive part is coming. That means the uncertainty will be very less when the spheromag rotation is very less. So that depends that if the MHD simulation we use a spheromag model, so depending on that how much rotation it has undergone, on the basis of that we can have different uncertainty things, and also that can be dependent on the initial density of the spheromag. So and as I already told that these structures are not attached to the sun, so you may get a double flux loop kind of structure, which I have shown here. So you can also see a positive part and also see a negative part, which does not exist in the real observations. So mostly the 90% of the cases of the events, we have seen that like there are evidences of the counter streaming of a bidirectional flow of electrons that actually depicts that the legs of a flux loop should be attached to the sun. So we have come up with a different approach where first we are embedding a toroidal kind of flux loop in a coronal magnetic field. So if we have a coronal background magnetic field, then we can embed this toroidal flux loop there. And then what we can do, we can use some advection profile where basically we can advect only the frontal part of this torus, not the back part. If we just only advect the frontal part of the torus, then with time it will take a kind of shape of this stretched torus-like structure. And as we are not advecting the backward part of this torus, so this backward part will always be remain stationary inside the inner boundary of the heliospheric domain, which is basically this gray shaded sphere here. So only the frontal part will come up from the lower boundary of the heliospheric model. So in that way, we can kind of mimic the shape of the CME that we observed. Or we can, in the most significant cases, we observe the CME should look like this. So we have tested these things for the same event, and then like the same event that I have shown with the spheromag. And here we can see we can observe only one unidirectional field from the observational output, which matches well with the observations. So this is because we are the structure is not detached from the sun. There are two legs always attached to the inner boundary of the heliosphere. We have also performed some analysis with the multi-spectrum events, and we got some very good matching, although the field strengths are not in the same scale here, but at least the orientation wise, we got some kind of good matching here. And we need to validate it for more and more events to get much more confidence about this method. Yeah, so with that, I would like to summarize the things that we have seen, that analytical model can be a very good tool because it can be run in a very quickly to predict the or to model the same structure from sun to earth. But there should be some caution, because most of the cases it when only the ICM is related to the isolated evolution, only those cases it can give you a very good results, but not for the other cases. And we have also seen for the self-similar expansion cases, the B naught, like the axial magnetic field, follows the 1/r square, but it is not valid for the other cases where the CM is not allowed for self-similar expansion due to the interaction with some high-speed streams. And also we have observed that if we have some multi-spectral observation, which are mostly radially aligned, then using the inner spacecraft observation, we can tightly constrain our model parameters so that we get very good prediction at the outer spacecraft. And we have also seen that there are pros and cons using the spheromech models. It can have very large rotations, which can give rise to very large uncertainty in the in situ results. And to overcome those, as because the most of the CM is the leg should be attached to the sun, so we have implemented a new approach with a new flux model for that. And the future work that I am doing here, we also wanted to see that how the flux loop under different topology will evolve in the heliospheric domain, that how will be the rotational effect will be for this flux loop, which will have different topology. So with that, I would like to thank you all, and yeah, any questions, please.
Thank you. Questions?
So
Mhm.
very interesting, this modeling. What causes a 90-degree rotation in heliospheric?
Yeah, so mostly if you see when we so basically there's a mismatch angle between the spheromagnetic moment and the background solar magnetic field orientation. So if you see the background magnetic solar wind is mostly purely radial, if you just neglect the Parker spiral rotational curve. So approximately it is purely radial. But when we launch the spheromag, so this when we launch the spheromag, that is, if we just go back here. Yeah, when we launch the spheromag, if you see the symmetry axis of the spheromag, which is mostly perpendicular to the radial direction here. So this is the symmetry axis of the spheromag, but the background magnetic field is purely radial. So almost there is a 90-degree mismatch in the angle. So then this symmetry axis is tried to align with the background magnetic field. That's why it is showing something.
That's the lens space.
Yeah.
So
Yeah.
the interaction between the
Interaction.
magnetic field.
Yeah.
So you would expect that if the twist in the spheromag changes, you think the rotation will be opposite?
Yeah, it is opposite. Yeah, because the study by Eliana's study, they have also changed the helicity sign, and they have observed that this rotation is opposite. Yeah.
Other questions?
Maybe two kind of related questions. The first one is, since you were addressing also space weather impacts and space weather effects, how automatic is the method? And the second related question to that is kind of, you have probably 3 parameters that you can tweak.
Yeah.
How much of this parameter tweaking is actually leading then to results that give you a good match with the actual observations? On how much of it is basically you just go in with what you observe, or how unique is the solution basically that you get?
Okay, so if we just go to this event. So I have tweaked the parameter, which is basically the exponent of the R, how the field strength should decrease with higher heliocentric distance. So in that particular case, what I have observed, there was not huge rotation or like deflection. It is only due to the interaction, or could be the rotation deflection, but at least by changing this exponent, I could get very good results for this particular thing. But if you go to the like MHD, there are lots of free parameters. So first thing is that you need to prepare your background solar wind properly before you are before injecting the flux slope there. So if you see there for this, for this, if you see the speed profile, you see there is very nice matching, right? So there I have to do a lot of iteration before producing this speed profile. So like not about the arrival time of the CME, but you can see there we have to match this high speed stream ahead, both like the arrival time of the high speed stream and also the magnitude of the high speed stream. So there are some input parameters itself in the WSA model which we can tweak to get to produce this. So once I produce this, then I start to inject MagTest flux slope model, and depending on that, if it has been rotated significantly, then I have to tweak the rotation of this flux slope here. But I think like for their, it is for this study, I have mostly used it to understand the physical properties, not in the aspect of the prediction purpose for this case. But I guess this kind of structure are more more important for the space weather implications, because the legs are attached. At least you can get rid of the huge rotation that is which the spheromag was experiencing. And in this case, I think the tweaking parameter again, the magnetic field strength, like the orientation more or less we can get from the tilt angle what we observe from the sun. But what we are also lagging about the field strength. So if you see, I have not scaled, so they are all scaled before comparing. So I have to tweak this, although there is a proxies through which we can constrain these parameters. So I have not looked it for these events yet, but to still that is the another tweaking parameter that we are not very confident about what will be the field strength and how that can be constrained from the near sun observation.
Any other question from online? Anyone? Okay, if there is no other question, let's thank our speaker again.